Okay, so this is an explanation of the red edge. So you know, as I have mentioned before also, that the absorption of plants and cyanobacteria, which have chlorophyll pigments and other pigments, is very strong, starting from about 200 nanometers all the way up to about 700. Then at 700, for some reason, stops absorbing and drops. The absorption drops very quickly. And so most of the light, in fact, is reflected. So what's not being absorbed is being reflected or transmitted. And this red edge seems to be a very prominent feature in many cyanobacteria and plants, as we'll see in a minute. So the question is, why is there a red edge? And this question has been bothering biologists for many years, and they don't really have a good explanation for it. Some of them say there's a red edge because in this region, wavelength region from about 700 to before water starts absorbing strongly, there are no electronic excited states of the molecules. But in fact, we know that's not true. In fact, there are some organisms which do in fact absorb strongly within this region beyond the red edge. So there is a possibility of providing pigments which do absorb in the range 700 to about 1,000 nanometers, but most of them don't. So the question is why? So if you have a camera which is sensitive to the infrared, then you can take pictures of trees in the infrared. And this is what your picture will look like. And they're very reflective, and that's why they are white in the infrared. Most of the photons are being reflected by the leaves, not at all being absorbed. And it's interesting also to note that the trunks, in fact, do still absorb in the infrared, but not the leaves. So this red edge is a characteristic of organisms which are exposed to the solar spectrum. So we have it for plants, and here what I'm plotting is this is the inverse of the reflection. So this is like here. Sorry, this is the inverse absorption. So this is the reflection. So here, below about 700 nanometers, we have very little reflection, and then at above 700, we get a drastic increase in reflection. This is for plants and aquatic plants, mosses, and the lichens also. And when we get to lichens, we see that the red edge is not so well defined here. Okay, and we'll explain why that is in a moment. But algae, for instance, also have a well-defined red edge. But these bacteria, for example, the purple bacteria and the green, which live best in low conditions of light, do not have a red edge. So it seems like that those organisms which are exposed to light, very strong light, have a very strong red edge. And those like the lichens and some of the bacteria do not have this very well-defined red edge. So that's a hint about what is possibly happening. So the red edge is an artifact of the maximization of entropy production or dissipation of the photons into heat. And it's due to pigments in water. Given the restrictions on these pigments, their size, and their dead time, okay, el tiempo muerto. So this is what this talk is going to try to prove to you today. So we come to this basic idea that plants and their appearance, proliferation, and persistence are really to optimize entropy production and not to do photosynthesis. So as we mentioned before, we have these other abiotic irreversible processes like hurricanes and the water cycle, and life, which is a biotic process, which is on the earth to increase the amount of entropy production. So what are some of the indications that nature does not optimize photosynthesis? Well, if you calculate photosynthetic efficiency of the plants, we only find that it ranges from about 0.1% to maximum of about 2%. So that is the energy, the free energy that plants have been able to obtain from sunlight with, in fact, very low efficiency, maximum 2%. Now, we as humans have built these photovoltaic cells, which have an efficiency between about 20 and 40%. So even humans can do better than plants, better than nature, which has had thousands of millions of years for evolution to increase the photosynthetic efficiency, but it's in fact remained very low. Okay, so that's an interesting fact. Also, we get the saturation effect. If we have more than 100 watts per square meter, which is only about 10% of the energy which the sun is giving to us, the sun is directly overhead, we're getting about 1,200 watts. So this is less than 10%, but we get a saturation in photosynthetic production of the storing of energy into carbon covalent bonding, or the photosynthesis saturates as we get to higher intensities of light. So we see we get very quickly to a saturation point at about 100 watts per square meter, which is much less than the energy that the soul is giving. And we also know that life plants reflect or transmit about 95% of the photons beyond about 700 nanometers. And it turns out that 700 nanometers is in fact where photosynthesis is most efficient. So around this wavelength, leaves of plants and cyanobacteria stop absorbing, but it is in fact where photosynthesis is most efficient. We know, for example, the chlorophyll molecule has an absorption about 430 nanometers, which is in the blue, and another absorption at about 680 nanometers, and which is getting to the red. And well, we know that this absorption in the blue at the short wavelength range, this light cannot be used for photosynthesis. It has to be dissipated to the red before it can be used. So only the light which is coming from the red peak, the absorption peak, or the light coming from the blue absorption peak in chlorophyll, which is dissipated to the red, can be used for photosynthesis. So it's only around this 700 nanometers where we get maximum photosynthetic efficiency. And yet, just a little bit beyond 700 nanometers, leaves reflect this light and don't even use it in the plant. And we also know that there are many pigments which absorb in the far UV. And and the question is, what are these pigments doing? Are they protecting? Or are they acting as antenna for photosynthesis? So we have a whole range of pigments which are absorbing from the far UV, that's in the UVC range, all the way up to 700 nanometers. And the question is, what are these pigments doing? The biologists say that these pigments are protecting the plant, okay, or they are antenna molecules which are helping to increase the photosynthesis. But if you look into that explanation in detail, you find in fact that they are not in fact protecting the plants, because plants can be exposed to this UV light and nothing happens to them. The photosynthetic efficiency at least does not drop. So they're not protecting the photosynthetic apparatus. Maybe some of them are being used as antenna. So they're collecting light in different wavelength regions and then dissipating this light to the infrared region, which can be used for photosynthesis at about 680 to 700 nanometers. So there are many indications that nature is not optimizing photosynthesis, but in fact, it seems to be optimizing the dissipation of light in all wavelength regions. So as I mentioned, then we can go here even to about 200 nanometers. We get still about 90% absorption. So this is from the book of Gates, which is absorption for different leaves is a function of wavelength. This is given in microns. So this 0.7 corresponds to 700 nanometers, which is the red edge. So we see that we get absorption about 90% over the whole wavelength region in the ultraviolet and in the visible. And then all of a sudden we get this red edge. So the idea today is try to explain the red edge. So what are some of these molecules which are absorbing over the whole range? Well, the fundamental molecules absorb principally in the UVC range, in the long wavelength UVC range. That means from about 220 nanometers to about 300 nanometers. So these include the nucleic acids. They include some of the amino acids and some of the fatty acids. And they have rather strong molar absorption coefficient. This means that they're absorbing very strongly. So many of the photons which are incident on these molecules gets absorbed. And their decay time is very rapid, about 10 to the 5 picoseconds, 10 to the 5 times 10 to the minus 12 seconds. As I mentioned, we also have these amino acids, which are also absorbing in this UVC range. They absorb a little bit longer wavelengths from about 240 to 200 or 300 nanometers here. And these are basically the aromatic amino acids, which means that they have this aromatic ring here. So they are tryptophan, tyrosine, phenylalanine, and histidine. They also have fairly strong absorption coefficient, but not as strong as the nucleic acid. Then we get into what are known as microsporines, and these are absorbing in the near UV. So, for instance, this microsporine here absorbs at about 300 to 375 nanometers. And we have different types which absorb a little bit longer wavelength regions. They also have very strong, this is almost the size of chlorophyll. So they're absorbing very strongly in this UV range. We also have the carotenoids, which absorb in the blue. They give rise to this yellow color, but these are pigments. And so these we can find in almost all the photosynthetic organisms, except in bacteria. And then we know we have the chlorophyll molecules, which are absorbing in the blue, about 420 to 470 nanometers, depending on the type of chlorophyll. And there's another peak, a second peak, within about 600 to 700 nanometers, where we have the red edge. And these are absorbing very strongly. And they have a lifetime of about 1 nanosecond. So this lifetime is important because once you absorb a photon, it goes to the excited state. And it depends how long it takes to go back to the ground state to be able to absorb another photon. If it's in the electronic excited state, it can no longer absorb photons. So the shorter this time period, the greater the system is at absorbing and dissipating, because it goes to the ground state and is ready to absorb another photon very quickly, in this case within 1 nanosecond. But if you remember, the nucleic acids have absorption times of picoseconds, even much faster than these chlorophyll molecules. We also have the flavonoids, which are absorbing in the yellow region, or the green region, about 550 nanometers. And this gives rise to these red colors that we see in the poppy, for example, in the flower, in the floor. So these again have very strong absorption coefficients, and they contribute to this absorption in the spectrum that we see over the full range. Now, so all of these organic molecules are absorbing in this range up to 700 nanometers. So we also have phycobilins, which absorb in the yellow and the red. So here again, we're going about to 700 nanometers. So we have all of these different types of pigments today, which are absorbing mostly in the range from about 200 nanometers all the way up to 700 nanometers. But if you look at 700 nanometers, so this is the spectrum of light which is arriving at Earth's surface today. And it's composed of 3 different components: the ultraviolet, which makes up about 9% of the free energy, and the visible, which contains about 40%. And then the infrared, which has about 51% of the free energy available. But if you look at where this border is here, the red edge, 700 nanometers, it's about here, we're missing all of the light in the infrared that's not being dissipated. So the question is, why do we have this border here at 700 nanometers, which is excluding about half of the amount of solar free energy? And in fact, excluding a lot of this region, which is very important for photosynthesis, where photosynthesis is most efficient. Remember, photosynthesis is very efficient around 600 to 700 nanometers. So then we're excluding all this region in which we should be able to have also photosynthesis with different molecules, which in fact we do. And I will show that, but not in all of the cases, not in the cases of those plants which are exposed to very strong light or very intense light. So this is the official explanation of the red edge, saying that these molecules, these pigments, for some reason, they don't give the reason, but for some reason, they don't have any intermediate states absorbing here. I've lost my pointer again, so I can't point to it, but you can see on the diagram on the left-hand side that we have these electronic states, the excited states, and then we have the vibrational states superimposed on the ground state. So they're suggesting that there are no electronic states which lie between these vibrational states and the first excited electronic state. But in fact, we know that's not true. So this is the explanation that the biologists give. In fact, we know that there are bacteria which do absorb beyond the red edge. So this is the red edge here. This is normal plants. They have a red edge at 700 nanometers and no more absorption. But if we go to bacterial chlorophyll, then we do get absorption in this red edge. So what's happening? Why aren't the plants also absorbing beyond 700 nanometers? Okay, so these are the different chlorophylls. And just by changing some of the molecules on the tail here, we can change the absorption spectrum to get absorption where the biologists are saying there are no electronic excited states, so there are no states which correspond to the absorption, and that's why there's this gap here beyond 700 nanometers. So this is some examples of bacteria which do in fact absorb, and not only absorb but also do photosynthesis beyond the red edge. So these are anoxygenic bacteria like the Heliobacteria, and the green and the green sulfur and the purple bacteria, they do photosynthesis at 840 nanometers. And this filamentous bacteria in the green, which absorbs at 870 nanometers, which is into the infrared. And this bacteria which absorbs at 960, and then we have even bacteria which absorb at 1000 nanometers and do their photosynthesis using these wavelength region. So it's not true that we cannot have pigments absorbing in this region beyond the red edge. So what kind of a absorption spectrum would you expect if nature was optimizing photosynthesis? Well, as I mentioned, we would expect an absorption spectrum something like this that absorbs around 700 or 600 to 800 nanometers, because that's where photosynthesis appears to be most efficient. It's actually 680 nanometers we get maximum efficiency for this photosynthesis. And so if we have this absorption spectrum like this, which we do not, our absorption spectrum is like the one at the bottom on the left-hand side, this spectrum. But if we assume that nature was optimizing photosynthesis, then we would have expected an absorption spectrum like this. And now, given the surface spectrum, which is this line here, this is the surface spectrum of light on the surface of Earth. And these gaps are due to the absorption of water in the atmosphere. Okay, this outer line is the spectrum incident on the atmosphere, in the upper atmosphere. But this inner line here is what happens when we arrive at the surface of Earth because of the absorption of the atmosphere. This is the case for a sunny day, and this is the case for a cloudy day. So if we convolute this absorption spectrum with the incident spectrum, then we should measure something like this. So if we are measuring the photosynthetic efficiency, then we should get something like this, if nature is optimizing photosynthesis. But if not, well, in fact, what we see is this. We have this absorption spectrum over the whole range up until the red edge, and convoluting that again with this spectrum at Earth surface, we get this. Now, so this is just putting this on top of this. We get a spectrum which looks something like this. So they're quite distinct. What would be expected if we were optimizing photosynthesis and the real case. And so what is the real case doing? Well, let's suppose that nature, instead of optimizing photosynthesis, optimizes entropy production. So let's try to do the calculation. So we can write an equation. I haven't mentioned this in the previous talks, but this is an equation which was given by Planck at the turn of the century, the 1900s. This is the entropy of an arbitrary beam of light, and this is given by the spectrum I as a function of lambda, the wavelength. So to get the total amount of entropy here over the spectrum, we just integrate over wavelength and over the solid angle which the source is emitting. So we can calculate what the entropy coming in to the system would be. That's the incident light from the sun, given the solar spectrum of the sun. So this is the solar spectrum of the sun at Earth's surface. Okay, this just accounts for the solid angle factor. Now, this is the radius of the sun squared over the distance between the Earth and the sun. That gives us the solid angle subtended by the sun on the Earth. Okay, and its spectrum, which you know is almost like a black body. So using the temperature of the sun, which is about 5,700 degrees Kelvin, we can calculate what is the incident spectrum and therefore calculate the entropy of the incident spectrum. And we can also do the same for the emitted spectrum by Earth. So given the temperature of Earth's surface, okay, and this black body equation for the spectrum, okay, we can calculate the flow of energy from Earth due to absorption of the incident spectrum and then emission. But we also have a part which is reflected or transmitted. Actually, for the Earth, we don't have any transmitted part. For a leaf, we do, but not for the Earth. And so we can calculate also this reflected and transmitted spectrum. It's again given by the temperature of the sun, but with a factor which is 1 minus A, the absorption, is the albedo. So that's how much is reflected. And we can do that knowing what the absorption is, you know, for the different regions of the absorption here. And then we can calculate what from this equation. So this is the total entropy production, which is the entropy due to the outgoing beam, which is emitted, which is due to this part. Okay, that part which is reflected, and minus the incoming entropy of the beam. And so that difference gives us the entropy production. These are intensities per unit time, per unit solid angle, and so on. So we have to do the integration of a solid angle, and we express the total entropy in terms per unit time. So we can do each of these parts separately, and this is what we find for the Earth, that the incident entropy in the beam of the incident light coming into Earth's surface is 0.069 watts per meter squared per Kelvin. And the emitted is 2.473 and the reflected 0.093. So putting that in this equation, we can calculate that the entropy production is just this due to the Earth. So we can do the same now for a leaf. Okay, but in a leaf, we also have a transmitted part, but we can include them together, the reflected and transmitted part, if we assume that the transmitted part also doesn't change its wavelength, stays as the same as the incident wavelength. It's just reflected or transmitted, so this part. So, but before we do that, we have to take into account that nature has also limits. Pigments have a finite area, finite size. So we cannot make pigments infinitely small. For example, in this carotenoid, they have a dimension of about 2 nanometers. And in the case of chlorophyll, it's about 3.5 by about 1.5 nanometers. So that gives us an area of about 5.25 nanometers. And well, we can not only just have pigments, but we also need support structures. So in the case of these chloroplasts, for instance, we can determine that only 5% of the chloroplasts correspond to pigments, and the rest 95% to the structure and to the water molecules which are around the pigments. So then, given this information, we can calculate that chlorophyll needs an area of about 5.25 nanometers squared, divided by, and only 5% of that is of the whole volume is being used by the chloroplast. So we do that to the 2/3 because we're taking like the ratio of the surface to the volume. And so that gives us that each of these chlorophyll molecules must occupy a space of about 38.7 square nanometers. Okay, and because we cannot pile one on top of the other and expect them to be absorbing similarly, then we can say that the maximum amount of, or the maximum areal density of chlorophyll, given its finite size, given these calculations, would be about 2.6 times 10 to the 16 per square meter. And people have done this calculation, in fact, and that turns out to be more or less the correct result. So we have about 2.6 times 10 to the 16 chlorophylls per square meter maximally. No? Because we need part of the volume for the support structures for the pigments, and also for water, which helps to dissipate pigments and therefore allow them to absorb another photon. Now, we also know that we have a dead time associated to these pigments. So, for example, the microsporines have a dead time of about 0.4 nanoseconds, while the chlorophyll have a dead time of about 1 nanosecond. So that means after absorbing a photon, they stay in the excited state. They can no longer absorb other photons until they drop to the ground state, which is at about 0.4 nanoseconds after, or in the case of chlorophyll, just less than 1 nanosecond. So we can assume that pigments, on average, take about 0.5 nanoseconds to go back to the ground state. So therefore, we can calculate how many photons these pigments could manage or handle, that is, absorb and dissipate. Okay, and you can convince yourself of this, that here we just the number over the time. Okay, this is the areal density over the time. This is the areal density we calculated on the previous slide here, 2.6 times 10 to the 16 meters squared over the time. And that gives us this value, which I can't see because there's a bar over it on my screen, but it looks like 3.5 times 10 to the 22 photons per second per meter squared. So that's the maximum rate that we can handle these photons coming from the sun, given their finite areas and given their finite dead time. Okay. So now, if we do the calculation, and we assume, because we're trying to optimize entropy production, so it's better to absorb photons of short wavelength than long wavelength, because dissipating photons of short wavelength, we're going to get more entropy production because we can convert them into more photons of longer wavelength. So if nature is optimizing entropy production, then it would start absorbing at the short wavelength region, which is in fact, we do find. And remember that, so this is just simulating. We do, this is the real spectrum measured, and this is the simulated spectrum in the program that I provide. And we just do the calculation. And given the fact that we can only absorb like 3.2 times 10 to the 22 photons per second per meter squared, 5 times 10 to 25, no? 5 times 10, not to 22, it's 5 times 10 to 25 photons per meter squared per second. And we start summing the intensities here, the number of photons at each wavelength. And when we get to 5 times 10 to the 25, we stop. Okay. And it turns out that this is where it is, exactly where the red edge is. So the red edge appears to be there because life has a finite size for pigments, and it has a finite lifetime for those pigments. So there's a limit to the number of photons that it can dissipate So it would start at the short wavelength side and then absorb photons until it came to its limit when it can no longer handle more photons because the system starts saturating. All the pigments are in the excited state and they can no longer absorb photons. And it turns out to give exactly the measured spectrum, absorption spectrum for plants. So this is rather a rough calculation, but it still gives us an idea that the red edge exists because of the limitations of absorption and dissipation. But that is assuming that nature is optimizing entropy production and not photosynthesis. Because if it was photosynthesis, then we would expect a spectrum which in fact looks like, where is it now? It looks like this, no? But in fact, we get one which looks like this. Okay. So this is our explanation of why we have the red edge, which, as I mentioned before, nobody has been able to explain very well. There has been no convincing explanation given for the existence of the red edge. And now that we know that it is entropy production rather than, but given the finite limits of size and lifetime, then we can now explain why those organisms which live at the surface floor, which are receiving very little light, like these lichens, why they don't have such a well-defined red edge like the others. Because these are not receiving the full photon spectrum. So they can produce pigments which are absorbing more towards the infrared to still increase entropy production. Okay. And we only have this red edge where we have plants or cyanobacteria exposed directly to the high intensity solar spectrum, because this is where it saturates. But if we have lichens which are living on the forest floor, which are receiving less intensity light, then they could still keep on absorbing and go into the red edges, which is what we saw. Okay, so that gives us a very nice. So the predictions then of this are that the environmental conditions determine, okay, especially the intensity of light, determine the position of the red edge. So for example, below the canopy or below water, where the intensity of the light is low, the lead edge can move towards the red. And this, in fact, we confirmed in this bacteria and lichen. At high latitudes, okay, where the intensity of light is also low, we can have the red edge moving towards the red. And this is still to be confirmed, but this is one of the predictions of our theory. And at high altitudes, where the intensity of the light would be greater, then this red edge would move towards the blue. Now, if there were some plants which had a high density of pigments, for example, if we didn't need so much space for the water and for the supporting material for the pigments, so we have plants with high density of these pigments, then we should get, according to our theory, the red edge moves towards the red.